If we have questions over any of the homework stuff, would we want to do this at the beginning or after we're done doing the other review that we're doing today?
I'm going to go over highlights of the units 2 through 4 in the humongous review sheet. And then after that, I will take any questions you have from any of the assignments.
Hi.
Hi, Zeus.
So which of those two will be our one grade for next week? Is it the humongous review packet or will it be those FRQs?
Like this week, I'll just put it together as one grade.
I want us to do, I guess, what is that, 3 parts technically, but 2 FRQs and then the review thing.
Review sheet, yeah. But like this week I posted the keys to both of this week's assignments on Tuesday. I'll do the same thing next week. So
Okay.
Throughout this entire time, you shouldn't have an issue finishing, or at least No, you shouldn't have an issue like finding the correct answers in time. I will post the keys on the Tuesdays before they're due, and I'll post the actual assignment the previous Wednesday, like I did this time. So, trying to give you plenty of time.
How are you doing?
I am good.
Are you sure?
Yeah. Getting a little stir crazy, of course, like I'm sure everyone is.
Yeah.
I've gone
Everyone's been so busy.
I've gone on lots of walks around the neighborhood just to get out of the house.
Oh, I think I saw you.
What?
No, I'm kidding.
I don't live in Cyprus. I've watched lots of TV. I've played a lot of Catan. Me and two friends have made online Catan Universe accounts, and we've played a lot of Settlers of Catan online lately.
It's pretty cool.
Yeah.
You play Minecraft?
No, I don't.
Lame. He's not part of our generation.
Okay, Minecraft was around when I was a kid. I just didn't play it.
Minecraft came out in 2010.
Yeah, I was in college. Kid.
That's not a kid. That's a college student. Make it sound like you were 10.
No, I wasn't. I just thought it came out longer ago. Okay. Roland, Roland Isaac, Jessica, John, Andrew. Yeah. I'll wait a few more minutes. But like before, it will also be recorded and posted online.
Some people already left.
Left.
Yeah, there was like 15 people earlier. Now there's 13 people.
I mean, they may be having internet issues. Okay, well, it's 1:05. Let's begin. So, as a reminder, anytime I share my screen, I can't see the chat window. So if you have a question, you can always unmute yourself and ask. Just click the little microphone next to your name and feel free to ask a question. But I can't see your question if you write it in the chat while I am sharing my screen. And before we begin the reviewing, I want to again remind you of some of the stuff that is on the Google Classroom. So at the Google Classroom, got some assignments, the humongous review sheet. I guess I could just delete the Taylor series video from this now. You should have watched it by now. If you haven't, watch it at some point. Very helpful. Got the humongous review sheet due next week. These AP Limits Review and Journey Through Calc due this Friday. And then these FRQs for next week that I already posted. And I'll post the keys to these FRQs sometime next week, probably next Tuesday, like I said earlier. I'll post the key to the humongous review sheet sometime next week as well. Although we will go over units 2 through 4 of it today. In the second stream, I want to again remind you about the YouTube channel. Where was the first time I posted the So it's in there multiple places. I've posted in the remind in multiple places, but AP Calculus BC, you can probably find this playlist by just searching that on YouTube. They started off by doing topics from Unit 9 that pertained to previous topics, so only 3 ideas. Then they did a lot of Unit 10 that covered more on what will be tested. And then this week, they started doing review. So starting with episode 14 earlier this week, they started doing review. Taylor polynomials and convergence tests, integration techniques. Today they did an Euler method one. And then from then on, tons of review videos all the way up until May 1st. And since now the test is May 12th, the guys doing it have talked about possibly doing it another week after that as well. These are extremely helpful to show you another way that they are helpful. If I go to this video, click show more, they have a lot of helpful resources right here at this link. You can go to their handouts. You just click the day. So if we want their handouts for that day, and a lot of helpful stuff here. Could even go there. And this first lists all the different series stuff that will be on the AP exam and just what they covered in that video. Very helpful. I would suggest watching these videos, or just certain ones that maybe you forgot how to do something. So just to remind you of those resources. Since we don't have actual in-person class, I can't teach full-on review of certain topic lessons. We're not going to meet every single day. My lessons again are mainly going to be going over the stuff I assigned to you. And so next week we'll start going over the FRQs that you are assigned. But if you need more resources, there's tons more resources online. You will be as prepared for the AP exam as you put into preparing for the AP exam, just like any year. Especially since, this year is going to be essentially open note, open book exam. But if there's something that you have to look up, then you're not ready. stuff that is a quick reference, like some sort of quick reference guide, like maybe this review sheet or our stuff you must know cold sheet, like those would be great to have next to you, just quick reference guides. But if you feel the need during the exam to look up something from our tons of packets of notes, then you're not ready. The purpose of all those notes is to study them ahead of time. If you have to look that up during the exam, well, that's going to be a waste of time. So prepare as much as possible ahead of time. So let's now look at the humongous review sheet. Okay, so we did some of this Unit 1 page last Wednesday. Again, if you're not in the Google Classroom, it's in BISB 5S. I think everyone is there now, or there's still maybe one person not. That'd be bad if you're not. But we did most of this page last week. I'll post the final thing of it next week. Then Unit 2, we already went over 1 through 4. I don't have a printer, so I only have one copy of this, and I already went over this with AB earlier, so some of this is already written down. So I will definitely go over all of it though, but it's just you just won't see me writing down all of it. But we already did 1 through 4 last week. These are the formal and alternate definitions of a derivative. Numbers 5, 7, and 8 talk about differentiability. 5, 7, and 8 talk about differentiability. And 5 asks, does a derivative at a point always exist? And really the answer is no. But the better way to answer this question is to list the ways a derivative does not exist. List the ways a derivative does not exist. So these here are the 3 ways a derivative does not exist. Either it is not continuous there. The only way for a derivative to exist is if it is continuous at that point. So if it's not continuous at that point, then the derivative doesn't exist there. If you have a vertical tangent at that point, then it doesn't exist there. If you have a corner, cusp, or sharp turn at that point, the derivative doesn't exist there, because that would mean that the derivative on the left side does not equal the same thing as the derivative on the right side. And so they're based on that. 7 and 8 ask, does differentiability imply continuity, or does continuity imply differentiability? Well, yes to number 7. If something is differentiable, it would automatically have to be continuous, because it has to be continuous to be differentiable. And number 8 asks, does continuity imply differentiability? No. So, I mean, because that statement's asking, if something is continuous, is it automatically differentiable? And that is no, because both of these pictures show examples of why not. At that point there and at that point there, it is continuous in these pictures, but we have a cusp, so not differentiable. We have vertical tangent, so not differentiable. Number 9 asks, let me move this real quick. There we go. Number 9 asks about the power rule, product rule, and quotient rule. So power rule, we should all know by now. Derivative of x to the n is n times x to the n minus 1. When the power comes down, subtracting from the power. So derivative of x to the 5th is 5x to the 4th. Derivative of the product of 2 things. The first times the second as is, plus derivative of the second times the first as is. Quotient rule. Low d high minus high d low, all low over low, low. So here would be the low, which is v times derivative of the top, which is u prime, minus the top times derivative of the bottom over v squared. On 11 and 12, my printer sucks, and so it didn't print the charts. I don't know why. So I just rewrote the charts. On number 11, I'd add e to the x. Add e to the x. You need to remember that one. I mean, you probably already have it memorized, so maybe it's not super necessary to rewrite it down. But if you have a to the x, so some number other than e, raised to the power x, derivative of that would be a to the x times natural log of the base a. So if natural log of x is 1 over x. And then for square root of x, well, square root of x is x to the 1/2. So we can apply power rule to that. 1/2 comes down, so 1 over 2. And then the new power ends up being 1 less, so x to the negative 1/2. Well, 1/2 is going to make it square root, and negative is going to put that square root of x in the denominator. So square root of x is 1 over 2 root x. So e to the x is e to the x. And you got all the trig derivatives, derivative of sine, cosine, derivative of cosine, negative sine, derivative tangent secant squared, derivative cosecant. My writing sucks. Negative cosecant cotangent, derivative secant secant tangent, derivative cotangent is negative cosecant squared. But you should also already know all these. Let's go on to number unit 3 and 4. So unit 3 is about differentiation still, but with composite functions, implicit and inverse functions. Composite functions are when you have a function inside of a function. So if you were to take the derivative of f of g of x, f of g of x is a composite function, and so that would need a chain rule. So we take the derivative of the outside, leaving the inside alone, and multiply by the derivative of the inside function. Then I have these two functions in red as my two examples. So the derivative of sine of x cubed, well, that would be cosine of x cubed, so derivative of the outside times the inside as is, times derivative of the inside. Then for x squared plus 2 to the 4th power, 4 will come down, parentheses stays as is, now to the 3rd power, times derivative 2 times 2x, which is the derivative of the inside. Implicit differentiation. That'd be like if we have x squared plus y squared equals 25, and we want to know what is dy dx, or y with respect to x. We could get that y by itself first, and then take derivative, but that's more extra steps. So we might want to do implicit differentiation anytime we have a function where x and y is going to be multiplied by each other or involved together on the same side of the equal sign. And that would mean we would just take the derivative of each term individually with respect to x, with remembering that y is a function of x. So derivative of x squared is 2x. Derivative of 2y would be 2y, but since y is a function of x, chain rule is involved, and got to multiply by dy dx. Derivative of 25 is 0. And then next you just get dy dx by itself, which would then give you negative x over y. Then number 3 is the same chart as the previous page, but now where things are not just x, they're a function of x. I usually write u there, but just using the same notation they have in this file. Derivative of a dx, well, like before, would be a to the f of x times natural log of the base a, but then because of chain rule, got to multiply by f prime of x. Back when we first learned this, we just usually used u there and then called the derivative of natural log of u prime over u, but with an f of x, there would be f prime over f. Derivative of square root of x, well, we said on the previous page that would be 1 over 2 root x, but instead of an x, we have an f of x, so instead of that x bar, we have f of x. And because the chain rule, it'd have to get multiplied by f prime of x, so then we got f prime on the top. Derivative of e to the f of x, well, that'd be e to the f of x times derivative of the function, so f prime of x. We haven't talked about number 4 in a long time. Number 4 asks us, what's the formula for derivative of the inverse of a function? Formula for the derivative of an inverse of a function. Well, given that f of x and g of x are inverses, then g prime of x would equal 1 over f prime of g of x. Would equal 1 over f prime of g of x. And it asks for an example, and since we haven't done this in so long, we could go over an example of that. I'll make one up real quick. So if we want, let's do this. If no, we'll call f of x we'll do that. F of x is square root of x. And we want to figure out what is g prime of, here's the inverse, so I'll put, let's go with g prime of 2. Okay, g prime of 2. Well, we need to know what g of 2 is, because we'll have to plug that into there. G of 2, well, f and g are inverses of each other, meaning f of what will give me 2? Well, f of 4 will give me 2. Meaning g of 2 must be 4. Okay. We need to know the derivative of f. So f prime of x, 1 over 2 root x. So then g prime of 2 would end up being, well, 1 over f prime of g of 2. Well, g of 2 is 4. So then we need f prime of 4. So that would end up being 1 over 2 times the square root of 4. So 1 over 2 times 2, which is 1/4. So f prime of 4 is 1/4. So then plugging that in, we'd end up with 1 over 1/4, which is 4. So just a quick reminder on that. Okay, then the trig inverse ones. I mean, you should also already have this written down somewhere. Sine inverse is 1 over square root of 1 minus x squared. Cosine inverse is just the negative of that, so negative 1 over square root of 1 minus x squared. Tangent inverse, 1 over 1 plus x squared. Cotangent is the opposite sign of that, so negative 1 over 1 plus x squared. Cosecant and secant, you're not going to see those, but that's what they are. 1 over x squared of x squared minus 1. Then negative of that. Really, I should have absolute value on that. There we go. Then higher order derivatives, that's just taking derivatives of derivatives. Don't forget like what the notation means on that. Since in BC, you'll guarantee to have a Taylor polynomial in test. You might see the terminology of the nth derivative like that at some point. Okay, unit 4. So, particle motion. Now again, we're not going to have unit 9 on the exam, but both unit 4 and unit 8 are on your exam. And so while displacement is just the difference in the position over time, another thing we can call displacement is also the integral of velocity from A to B. dt. So the integral from A to B of velocity, which, because of fundamental theorem of calculus, would be the position at time B minus position at time A, is also displacement. Velocity is the first derivative of position, so velocity at a certain time, just derivative of that. Speed is the absolute value or magnitude of velocity. Acceleration is the second derivative of position, and first derivative of velocity. We should all already know that. Okay, number 2 is asking about related rates problems. First, how you recognize them. Well, to recognize a related rate problem, it's going to be involving multiple rates. And what I mean by that is, most likely, if something's a related rates problem, they would mention a rate somewhere, and they would probably ask you for a rate. Or maybe they'll mention 2 different rates. Either they would mention multiple rates in the problem, or they would mention that the rate of something is like 5 meters per second and ask for the rate of something else. So there's multiple rates involved in the scenario for the related rates problem. And here are some steps that we went over originally to do a related rates problem. First, I'd highly suggest a picture. Almost all related rates problems need a picture, because they're almost always geometry based. Then you need to make an equation relating your variables. You would make an equation relating your variables. If you're dealing with sides of a triangle, you would use Pythagorean theorem. If you're dealing with the circumference of something and the radius of something, you'd use the formula for circumference and so on. Just you'd come up with an equation that relates the variables. Step 3, differentiate implicitly with respect to time. So by implicitly, that means you're going to differentiate each term individually with respect to time, meaning every single variable is then a function of time. So I have an example over here in blue. So if we're dealing with the circle x squared plus y squared equals 25, maybe we're talking about the rate at which the x value changes and the rate at which the y value changes. You might be told one of those and asked for the other one at a certain point value. Well, then you would take derivative of x squared with respect to time, which would give you 2x times dxdt. Derivative of y squared with respect to time would give you 2y times dy dt. And derivative of 25 is 0. And then you plug in any given information and then solve for what you're asked to solve for. Okay. And remember, you should have like your tests, your notes, your homework from throughout the entire year, and all those keys are still posted online. Maybe if you still want to find the key from something previously in the year, under the resources tab on my class website, I have the calendar from the fall semester. So that is still available. For related razor problems, any formulas from geometry you might want to remember is just any 2D formula that could become necessary, any two-dimensional formula, such as Pythagorean theorem, area of a circle, circumference, area of a triangle. Any two-dimensional formula would definitely be helpful for that. They will give you any 3D formula that you might need. So if it's a cone or a sphere or a cylinder, they'd give you the formula for a 3D shape. Okay, number 4, approximating the volume of a function using a tangent line. Well, first, let's remind ourselves what the formula for a tangent line is. Well, a tangent line in general in point slope form is this right here. Y minus f of a, which is the y value at the point, equals f prime of a, which is the derivative at the point, times x minus a, which is the x value at the point. And so if you wanted that equation, solve for y by itself, just throw that f of a over to the other side. I made up the scenario in red that if we have this function x squared plus x and we want to approximate f of 1.2. Well, if you're not told what to approximate, just come up with an easy value near that point. So I used f of 1. That's a nice easy value near that point, and f of 1 would end up being 2. We would also need the derivative, because you got to be able to figure out the derivative at that point for the tangent line. So derivative was 2x plus 1, so then derivative at 1 ends up being 3. Then just plug that stuff in. So f of a was 2, f prime of a, 3, then x minus 1. So then that right there, that's just the tangent line. Haven't done the approximation yet. That's just the tangent line through the function at the point x equals 1. Then right here in green, I then plugged in 1.2 into x and solved and got y is 2.6. So 2.6 is an approximation for what the function at 1.2 might be. On a tangent line approximation problem, you might also be asked to come up with whether it's an overestimate or underestimate. Well, if something is concave up, the entire tangent line would be below the curve, making it an underestimate. Something concave down, the tangent line would be above the curve, causing it to be an overestimate. And this particular one, well, the second derivative is just a positive 2, so that's one way to know that it's concave up. Another way is just it's a positive quadratic. That's also making it concave up. So this tangent line would be an underestimate. This one would be an underestimate. And then L'Hopital's rule. If the limit is exponentially of fx over g of x is either 0 over 0 or infinity over infinity, I mean, it could be plus or minus on the infinities, that doesn't matter. So that right there means indeterminate. Indeterminate doesn't mean you're done. You can still figure it out by doing L'Hopital's rule, which tells us that then the limit as experts say of fx over gx is the limit over x approaches a of f prime of x over g prime of x. And then I got these two examples here. First one's using a rule that we really should know. Limit as x approaches a of sine of x over x. Both top and bottom go to 0. This is correct notation for how you want to do this. you want to point with arrows. They don't want to see equals 0 over 0. They don't want to see that because that means nothing and is not accurate. It doesn't equal 0 over 0. So we say that the top and bottom are going towards 0. Then we say that we are using L'Hopital's rule, and so that because we're using L'Hopital's rule, then also equals limit as x approaches a of cosine over 1. Because the root of the top is cosine, the root of the bottom is 1, so 1. And same idea over here. Show the top and bottom are going towards 0 with arrows towards 0. Say that you're using L'Hopital's rule, so I got an LH there for that. Limit as x approaches 2 of 2x over 1, because the top is 2x, the bottom is 1, so it equals 4. Okay, so went over a lot of units 2 through 4 on the Humongous Limits Review. Went over units 5 and 6 from this review sheet on Friday. But right now, do you have any questions from the limits review page or the Journey Through Calc page? Any questions from either the limits review or Journey Through Calc?
I have a few from each of them, but my first one would be 9C on the limits review.
9C on limits review. Okay, I did that one earlier, I think. I did, yeah. AB asked about that. Cool. And I remember the answer. So on all of 9A through B, we want, I'm going to move this over to the left. There we go. Move that down a little too. No, not right there. Okay, that works. On all of 9A through B, as it says right here, the limit as x approaches c of f of x exists if and only if the limit as x approaches c from the left of f equals limit as x approaches c from the right of f. And this is a very important concept to remember. I mean, that's pretty much the definition of a limit for one to exist. But that's very important to remember anytime you have limits of a combination of functions. Anytime you have a limit of the combination of functions, you want to use that idea. For all of limits for 9A through C, you have to find the limit as x approaches a from the left, or c, whatever variable you want to call that, and the limit as x approaches c from the right. And then if they're both the same, then they are equal to each other. So I'll show it for 9C. So if I'm doing that on 9C, we then have the limit as x approaches 1 on the left of g of x plus 2 plus f of x. So if I was to show all steps here, well, if I now substitute, that's now looking at as x approaches 1 on the left. As x is approaching 1 on the left, that's looking at the left side. I could maybe put it like this: g of 3 on the left plus f of 1 on the, not that, plus f of 1 on the left. Well, g of 3 on the left is a 3 plus f of 1 on the left is a 1. So that is 4. And then if we look at the limit from the right, the limit as x approaches 1 on the right of g of x plus 2 plus f of x. Well, that, now if we look at things from the right, I won't do both steps this time. We should be getting the idea. So now we're going to look at the right side as g is approaching 3, because putting in the 1, that's then g of 3. as as x is approaching g from the right side, well, that is 2. That is 2. And then as f is approaching 1 on the right, as x is approaching 1 on the right side for f, which is also 2. And that equals 4. Well, both of these are the same. Since those are both the same, the overall limit is 4. And so that's the steps and process you would do for 9a, b, and c. You want to find the limit on the left and the limit on the right of the entire thing. Okay, since we're already on this worksheet, any other questions from the limits review? What other questions from the limits review?
18C.
18C, let's scroll down to 18. Is this 18 right here? Yeah, that's 18. I'll put y'all right there. Okay, so in 18C, I'm going to check real quick. What did we have as the answer? Make sure I tell you all right.
Hello?
Yeah, I'm here. Okay. So on horizontal asymptote problems, as it says right here, some of these are easy to find, such as on A and B, you can just think your end behavior rules to figure out the horizontal asymptote. But C, not that easy. So the limit as x approaches infinity, positive infinity and negative infinity, that tells you what your horizontal asymptotes are. And so on 18C, if we take the easy to see one first, limit as x approaches negative infinity of 2 to the x power plus 3 over 5 minus 3 to the x power. Well, as x goes towards negative infinity, that means 2 is being raised to a power of negative infinity, and 3 is being raised to a power of negative infinity. If you raise something to a negative infinity power, I mean, that will end up kind of looking like 2 to the negative infinity plus 3, 5 minus 3 to the negative infinity. When you have a negative exponent, well, it's really 1 over 2 to the infinity, which is 0. So that term goes towards 0, which is just going to leave 3 on the top. And that term goes towards 0, which is just going to leave 5 on the bottom. So we have, going towards the left, going towards negative infinity, we have a horizontal asymptote of 3 halves. So y equals 3 fifths. 3 fifths is one of them. And let's look at the other direction, going towards the right. I'm going to change different colors. Okay. Oh, why didn't it move? Okay, going to the right, I'm going to be limit as x approaches positive infinity of 2 to the x plus 3 over 5 minus 3 to the x. Okay, well, it looked like we have 2 to the infinity plus 3 over 5 minus 3 to the infinity. And that's hard to really tell what's happening there. We could try L'Hopital's rule, because it looks kind of like the top is going towards infinity and the bottom is going towards infinity. So if we try L'Hopital's rule, then we would have, well, derivative of 2 to the x would then be 2 to the x natural log of 2 over a, then derivative 3 is just 0. Derivative 5 is 0. We should have still limit notation here. Limit as x approaches infinity. Negative 3 to the x natural log of 3.
Well,
I originally thought it was just bottom heavy, like going to 0.
Yeah, but the top is doing enough. Well, this could just keep doing L'Hopital's rule over and over and over again.
well.
The fraction is getting smaller though, right? As you're increasing x. Because then it goes like if x is 1, it starts at 2/3, then 4/9, then 8 over 27.
Also, if you do L'Hopital's rule multiple times, the fraction becomes more clear that it's bottom heavy.
Well, I got that key from somebody else.
That's why I was
I think I'm
confused.
going to go with 0. I was trying to figure out how they got that answer, but
It's 2/3 raised to the x. That's another way to write that, but that doesn't tell you anything about end behavior.
oh yeah, that was stupid. I was being stupid. No, you're right. We can just write that at towards infinity. That really is just 2/3 raised to the x, raised to the x power. But then that's going to end up being 0. Like just, it's going to go towards 0. Like as we get off towards positive infinity. It is, yeah, it's bottom heavy. That should have been y equals 0 as the other one. Or if it is 2/3, I don't know how they got that.
I had one more question for this particular packet. It was number 27, but I think that was just because it said the limit was still a function of x. But whenever we still,
This is definition of derivative.
right. So then we take the
because
derivative.
if we look at 27, this section right here,
He's so excited.
that is like looking at f of x plus h. And where this parenthesis over here is f of x. And so this is limit as h approaches 0 of f of x plus h minus f of x all over h. And that is the derivative of a function. So what we really need to do is identify that that's definition of derivative, figure out what the function is talking about, and then take its derivative. But if we want to actually use a limit notation, I mean, because we learned this the first time before we knew derivatives, we could actually multiply out the top limit as h approaches 0. Well, x plus h squared is x squared plus 2x h plus h squared minus 3x minus 3h minus x squared plus 3x all over h. I'm going to change colors to cancel stuff. Okay, so we got a positive x squared canceling with a negative x squared, a positive 3x canceling with a negative 3x. Then this h in the denominator can cancel with one h from each term in the top. So that can cancel with that h right there, the squared part of that h, and that h right there, which then leaves limit as h approaches 0 of, we just got a 2x there. We got an h still right there. We got a minus 3 right there. Okay, well now limit as h per 0 of this, well, that term would just go away. It's just left with 2x minus 3, which we already know should be the answer if we identify that our function, if we identify that our function is x squared minus 3x, and we're just taking its derivative, well, derivative of x squared minus 3x is 2x minus 3. Any other questions on the limits review? Okay, well, let's move on to the Journey Through Calc. Any questions on the Journey Through Calc worksheet?
Letter R.
Letter R. Okay.
I had a question on I.
R and I. Well, already heading there, so I'll do R first. We want R and we want I. Okay, so R, X number of people in thousands inside the amusement park, number of people inside the amusement park that have contracted a virus can be modeled by V of X. Okay. V of X equals H of X over re-X. Okay. Then we're asked the number of people in the park. Number of people in the park is increasing at a constant rate of 0.2 thousands of people per minute. Okay, well, I can call that its own rate. So let me show you what I'm writing here. They gave us this, which tells us the number of people who have the virus at any point in time, right? That's what they said. The number of people, the number of people inside a park who have the virus, is the V of X. And then that 0.2 thousands of people per minute, 0.2 people per minute, well, we're calling X the number of people. So if X is number of people, then this 0.2 people per minute could be dx dt. That could be dx dt. And we are asked, so using this model, what is the rate that people inside the park are contracting the virus with respect to time? With respect to time when there are 4,000 people in the park. So what that is specifically asking, so they gave us this function, which tells us people in park with virus. And then they told us that the rate of people in the park, of going into the park, is 0.2 people per minute. And they are asking for the rate at which people are contracting the virus with respect to time at time t equals 4, meaning they are asking for dv dt at time 4. They're asking for dv dt at time 4. Well,
Would it be X equals 4 since it's when the people is 4,000?
wait, people 4,000. Did I write that? Let me look back. Oh yeah, when x is 4. When x is 4. Okay, yeah, that makes more sense. Well, so that's what we want to know. That right there is what we want to know, dv dt at x equals 4. Well, dv dt, well, that is dv dx times dx dt. I wrote that wrong again. There we go. dv dx times dx dt. Because then the x's will cancel and you just both be dv dt. So we need to figure out what dv dx is. We need to figure out what dx dt is. Multiply them and then plug in the form for x. So dv dx. Well, that's just derivative of the velocity. I mean, not the velocity, of the virus with respect to x. So derivative of this function here. Well, gotta use chain rule. Not, well, and chain rule, yes, and quotient rule. So low d high, low is 3x times root of the top is h prime of x minus high d low all over low squared, so 9x squared. And then we will end up multiplying by dx dt, which is 0.2, meaning dv dt would be 3x h prime of x minus h of x times 3 over 9x squared times 0.2, which is dx dt. And so if we want dv dt at x equals 4, we just need to plug in 4 now, dv dt at x equals 4. Okay, well, 4 right here, that gives us 12 h prime of x, no, h prime of 4 minus h of 4 times 3 all over 9 times 4 squared. Well, 4 squared is 16. 9 times 16 is 144. And then that whole thing will get multiplied by 0.2. Okay, well, we need to identify what h prime of 4 is and h of 4. Then we could really just stop there after we plug in stuff for h prime of 4 and h of 4. So h prime of 4 and h of 4. Let's go back and look at the given information. Well, so we are looking at the h function, which is the piecewise when x is 4. Well, when x is 4, h of 4, we can just plug it into the section where x is greater than 3. So that will end up being 4 e to the, guess, what, e squared, because 2 times 4 minus 6, minus 16 plus 5. So just 4e squared minus 11 is h of 4, then h prime of 4. Well, we would take its derivative and plug in 4. So its derivative, let me write that. It's going to be 8e to 8. Yeah, still e squared. Minus 2x minus 2 times 4, so minus 8. And that'd be it. So you can see what I wrote. So h of 4, I just plugged 4 into the h expression. We get 4e squared minus 11. Plug 4 into the h prime. We got 8e squared minus 8. I just plug that in now and then to just stop. So we have 12 8e squared minus 8 minus 3 4e squared minus 16, no, minus 11. All over 144 times 0.2. That should be equal to the answer they had. I really hope so.
That's the answer I had, but it was like see how they have 0.07? I got 0.7.
Well, honestly, if you got what I have, that's the answer they wrote slightly before, like 3 steps before the 0.077 is what I wrote down. And can you stop at that point on the AP exam? Yes. So I don't know if I made a calculator mistake or not, or if you did. I could check my calculator, what we get, if you want me to. But on the actual AP exam, I would just stop right. Where'd it go?
That's why I'm thinking it was a
I
mistype
would just
there,
stop
because I
right
got the
there
same
because you
thing.
don't have to simplify.
Right, I had the same thing there, yeah. Just don't know how to
And that is
simplify
what they
that
had on the
last
key as well.
Just don't get how they simplified it, because I was trying to check that answer exactly, but it was like a power of 10 off or something like that. It was weird.
Well, and this right here ends up being 12e squared minus 33 this how'd they simplify it next? They said 28e squared minus 21, then over 48 times 50. Well, they ended up with 50 on the bottom because 0.2 is 1 over 50. So that's where they got the 50 on in the denominator, because 0.2 is 1 over 50.
Isn't it 1 over 5?
Oh, it is. That's where they made the mistake. That's how they made a mistake. They have 50 on the bottom where they should have only had a 5. That's where how you were 1/10 off.
Okay.
10 times off. So they made the mistake there.
Yeah, okay.
And so that's another reason why you just don't simplify always, because that's an easy 0.02 would be 1 over 50, but they wrote 1 over 50 for that, and it should have been 1 over 5. So.
But then, yeah, I don't know, but plus the 48, where does that come from? I mean, 12, if they're breaking down 12 squared, not into 144, I don't know what they're doing.
Oh, well, they simplified everything into, they got the 148 by, we have this 12 right here, that 3 right there, that 144. If I just simplify by 3 everything, 148 divided by 3, 144 divided by 3 is 48. And that 3 cancels, that becomes just 4.
Oh, gotcha.
Dividing top and bottom by 3. And then at that point, well, we have 4 times 8, which is 32. 32 minus that 4 leaves the 28e squared. 4 times 8, 32. 32 plus 11, right? Yeah, that would end up being plus 11. It's 44, which is what they had, right? They had minus 21. Oh, no, that'd be, oh, because that'd be minus 32 and plus 11. So yeah, minus 21. Then all over the 48. Then you should also have a 5 in the denominator as well. But again, you could have just left it as how I boxed it with the blue. No reason to simplify if you don't have to. Clearly, someone who made the question made a very easy mistake, so you could as well. Okay, then Qua asked about letter I, right? Letter I. You can see what was letter I. Letter I, evaluate integral from 0 to 7 of f prime. Zero to 7 of f prime of x. Okay, well, I guess they would have to give us f information. Oh, well, this is a definite integral. The definite integral from a to b of a function is the area under that function from a to b. So this right here is asking for the area under f prime starting at x equals 0 till we get to x equals 7. Well, the graph they gave us is the f prime graph. They gave us the f prime graph. And so we just need to come up with the area under f prime starting at 0, ending at 7. We might want to split it up a little bit at certain spots, but all we're really doing is finding the area between the function and the x-axis starting at 0, ending at 7. So, I mean, I could split it up, integral from 0 to 2 of f prime, because that section is definitely going to be a different scenario than this piece. Then plus integral from 2 to 4 of f prime, plus integral from 4 to 5 of f prime, plus integral from 5 to 7 of f prime. I split it up like that because that's all the different pieces. It's all the different pieces of our function where the graph changes what's happening. The integral from 0 to 2 of f prime is below that semicircle. It's below that semicircle. So that section, integral from 0 to 2 of f prime, would be, well, for that section, I'd take that entire 2 by 2 square, which would be 4, and then subtract, well, not semicircle, quarter circle, and then subtract that quarter circle. Well, that quarter circle would be pi times 2 squared divided by 4. Pi times 2 squared divided by 4. 2 squared is 4, divided by 4 would just be pi. So the integral from 0 to 2 of f prime would just be 4 minus pi. And plus integral from 2 to 4, well, it's just the area of this triangle, which would be 2 times 2 divided by 2, which is 2. And plus integral from 4 to 5 of f prime, well, that's this section right here. Well, that's going to be negative 1/2, negative 1/2. And plus the integral from 5 to 7, well, that's this rectangle area from 5 to 7 of f prime, so that's 4. Then you can just add all of that together. You got that 4 and that 4, so 8 plus 2 is 10. 10 minus 1/2 That could be 19 halves minus pi. Yeah, that's what they got. Okay. Well, it has been a while now. Again, the keys are posted. You can email me any other questions you have, but I don't want to take up too much of your time. It's been an hour since I actually started teaching. We will meet again on Friday. I'll go over sections 5 and 6 of the giant review sheet and then continue to answer any other questions you have. Could be from these two worksheets, or if you already start anything else. And if you don't have more questions, maybe I'll also go over unit 7 on the review sheet. But that will be it for today. Any final questions before we end? Logan, I miss you guys too. I can't stress that enough. I miss all of you. This scenario really sucks. And it's definitely likely the next time I could see you is at graduation in July. Which, yes, again, sucks. And well, I guess Zeus, if you want to still walk the stage, you'll have to come back. Well, what? What does that mean, Logan? Oh. One thing I was thinking of doing sometime in June or July, once quarantine is over, I'll come to like the Cypress Mod Pizza or Chick-fil-A or something, and we just all hang out. Yeah, Nola, you should. That'd be cool. Okay, well, guys, oh, one other thing. Saturday is my birthday, and if you want to get me a gift, I think it'd be pretty cool if you made a meme either about math in general, calculus, or my class, or our class, just to make me and your friends laugh. So a meme about calculus or our class would be pretty cool for my birthday. Well, see you guys. Bye.
Bye.
Bye-bye.